Good morning, all of you. Today we are moving to a new lesson, that is waves. Okay, so you know what is a wave. So, how will you define a wave? Waves occur when a system is disturbed from its equilibrium position, isn't it? For example, when you throw stone into water, you can see the water waves because that point is disturbed, and this disturbance travels, or you can say propagates, from one region of the system to other. Okay, so how can you define wave? Yes, waves occur when a system is disturbed from its equilibrium position and this disturbance travels or propagates from one region of the system to another. Clear? Now, as you know, when you put a stone into a pool of water, waves will occur and it will move like this. The movement of the wave, we call it as propagation of the wave. Okay, so while it propagates, it actually transports energy and momentum from one part of the medium to the other part. Understood? But there is no motion of the matter or motion of the material of the medium. Understood? That is, in a wave, both the information and energy from one point to another is moved or propagated, but there is no motion of matter as a whole through a medium. Understood? Now, the types of waves you can classify into three. Mainly, you can classify into three. The first one is mechanical wave. Second one is electromagnetic wave. And the third one is matter wave. Okay, the waves can be classified into three: mechanical wave, electromagnetic wave, and matter waves. So this electromagnetic wave and matter wave, just you understand the definition here. You will study it in detail in your 12th standard. Okay, so anyway, first we'll move to mechanical waves. Mechanical waves means the waves requiring a material medium for its propagation. Understood? The waves which require a material medium for its propagation, that they are known as mechanical waves. So you can say the examples like sound waves, then water waves, then seismic wave. Okay, these are the waves which require a material medium. Okay, sound needs a medium for propagation, that you know, right? So these waves are also called as elastic waves because their propagation actually depend on the material media, understood, which possess elasticity and inertia. These are the properties which a material have, and on that properties or that particular material, these waves depend, and so they are known as elastic waves. So generally you can say mechanical waves are the waves which require a material medium for its propagation, and you have to know some examples like water waves, then water waves, then the second one is sound waves, then seismic waves, etc. Clear? These are the examples for mechanical waves. Okay. Now the second type of wave is electromagnetic wave. In your 12th standard, you have a chapter for this electromagnetic wave. So here we just know the basic knowledge. That is, electromagnetic waves means these waves travel in the form of oscillating electric and magnetic fields, and they do not require a material medium. They do not require a material medium for the propagation. And how do they propagate? They propagate in the form of electric, okay, and magnetic fields. This is the diagram for an electromagnetic wave in which there are both fields, electric field as well as magnetic field. They are oscillating fields. So detailed study you will have in your next year. Now just understand that these electromagnetic waves do not require a material medium. Understood? So many examples you may have studied for electromagnetic waves like gamma, then X-ray, UV, infrared. These are microwaves, radio waves. These are all examples for electromagnetic waves. They do not require a medium. Even the visible light is an example for electromagnetic wave. Understood. Now the third type is matter waves, and in matter waves, these waves are associated with microscopic particles like electrons, okay, then protons, etc. These are the microscopic particles, and these waves are associated with these microscopic particles. That means there are some fundamental particles, like electrons, protons, or even atoms, molecules, etc. When they are in motion, such waves are known as matter waves. And it was actually introduced by a scientist named de Broglie. So these waves are also known as de Broglie waves. Okay, that also you will study in your 12th standard. So these are the types of waves. Clear for you? Okay. Now, based on the medium of, based on the propagation of waves, the waves are classified into two. They are transverse waves and longitudinal waves. Okay, so this is based on the way of propagation, how they are moving. Okay, so first of all we'll discuss transverse wave, in which the particles of the medium execute simple harmonic motion that you have studied about their mean positions in a direction perpendicular to direction of propagation. Which means, if a wave moves like this, okay, so many particles are vibrating in this particular motion, isn't it? That means the movement of the particles is actually in this way. The direction of propagation is in this direction, and the movement of the particles is actually perpendicular, okay, perpendicular to the direction of propagation. Clear for you? The movement of the particles is perpendicular to the direction of propagation. Such waves are known as transverse waves. Like the waves produced in spring, then the ripples on the surface of water. Understood? Then the musical instruments. In the musical instruments, stringed musical instruments like guitar. In such musical instruments, you can see the movement of string in this way. That means the individual particles which are in motion, or in that particular medium, whenever you are considering individual particles, they execute the motion which is perpendicular about the mean positions, perpendicular to the direction of propagation. Understood? That type of motion is known as transverse motion, and such waves are known as transverse waves. So how can you define? It is the wave motion in which the individual particles of the medium execute simple harmonic motion about their mean position in a direction perpendicular to the direction of propagation of the wave. Okay, so that is transverse wave, and the examples are waves produced in a string, then ripples on the surface of water, etc. Clear? That means when you are fixing a string on a particular point and you are stretching the string and releasing, you can see a wave produced on it. And in this wave motion, you can see the particles, they are vibrating like this about their mean position, which means the particles which are in motion are perpendicular to the direction of propagation. This is the direction of propagation. Waves are propagating in this direction, isn't it? So each particle is perpendicular to the direction of propagation. That is called transverse wave. Okay. Now the second one is longitudinal wave. And in longitudinal wave, the best example is sound wave. Okay, sound wave is an example for longitudinal wave. Then the waves produced in spring. So these are examples for longitudinal wave. And in longitudinal wave, you can say that the individual particles of the medium which execute simple harmonic motion about their mean position along the direction of propagation of the wave. Okay, which means along the direction means parallel to the propagation of wave. For example, if there is a long pipe like this and it is filled with air, you can assume that. Okay, now here this is a long pipe which is filled with air. Here I have a piston at one end, and if you push the piston suddenly, here a small layer of air just near this piston is compressed, isn't it? And after being compressed, this layer moves towards right and compress the next layer and so on. So this compression will reach the other end. Clear? That means I am pushing this piston towards right side. So the air near this area will get compressed. Again, this compression will in turn compress towards the right side. So here this layer also get compressed, and this will continue till it reaches this end. Isn't it? Thus, the motion of the air and the changes in the air pressure travel towards the right as a pulse. Okay. Now if the piston is pushed towards left side, what will happen? As there is rarefied in the layer adjacent to the piston occurred, resulting in the fall of pressure. You will release, no? So compression will get reduced. That is called rarefaction. Okay. So there is a pulse again produced, isn't it? In the other direction or in the next. That means compression as well as when you release means there is a release. That means there is a rarefaction. Understood? So due to continuous pushing and pulling of the piston in a simple harmonic manner, a sinusoidal wave, that means a sine wave, okay, travels in the cylinder in the form of compressions and rarefactions. Understood? Resulting a temporary reduction in the volume and consequent increase in density. Understood? Here the propagation is parallel like this way. Here it is perpendicular to the direction of propagation. Here in this way it is propagating. That means in some area it is getting compressed. In some area it is getting rarefied. Understood? So the such area having high pressure, they are known as compressions. And having low pressure region, they are known as rarefactions. Again compression, rarefaction, in such a way it will move. Understood? So you can say a compression means it is a region of the medium in which the distance between any two consecutive particles of the medium is less than the normal distance, which means they are tightly packed. Okay. Now again, in the next region, rarefaction means it is a region of the medium in which the distance between any two consecutive particles of the medium is more than the normal distance. Such a region is known as rarefaction. So in a longitudinal wave, both compressions and rarefactions exist. Okay. And in the case of transverse wave that we have already discussed, you can see there is an upper region as well as lower region, and this upper region is having a maximum displacement at this point. Lower region has a maximum displacement at this point. Okay, so this upper region or the region in the upward direction, we call it as crest, and this region we call it as trough. So one crest and one trough will constitute a wave, one wave or one oscillation. Clear? This is the crest and this is the trough in the case of transverse wave. And in the case of longitudinal wave, we have compressions and rarefactions. Understood? Compressions means a region like this, high pressure. Then rarefactions means there is a relaxation. Okay, again compressions and rarefactions. In such a way, you can represent the regions in a longitudinal wave. Hope you understood the differentiation between this crest and trough as well as compressions and rarefactions. Okay. So next is displacement relation in a progressive wave. That means if we want to describe a traveling wave in mathematical form, in equation form, we need the position x and time t. That means when time t equal to 0, the wave was starting, just it was about to start, and after a time interval t, the wave moved to a particular distance, and that is actually the, if suppose from this point it traveled and after a time t it reached somewhere here, this is actually the position, isn't it? Position x of the wave. So in order to describe a traveling wave mathematically, we need two things. They are the position as well as time. Okay. Suppose you consider a wave traveling in this direction, that is in the x-axis, positive x direction. This is the positive x direction. Okay. Now, the displacement you can denote as y. Displacement, this displacement actually denotes the transverse displacement of the element at position x at time t. Okay, this displacement is given by a relation like this, that is y of xt is equal to a sine kx minus omega t plus phi. Yxt is equal to a sine kx minus omega t plus phi. Okay. And here the above equation can also be represented by using the combinations of sine and cosine functions, like a sine kx minus omega t plus b cos kx minus omega t, where this a is actually root of a squared plus b squared. This is actually the amplitudes, okay? These are the amplitudes of the wave. Then phi is equal to the angle. This value is equal to tan inverse b by a. Okay. So for a traveling wave, the equation is a sine kx minus omega t plus phi. Again, you can write this equation in the form of sine and cosine, like capital A sine kx minus omega t plus b cos kx minus omega t, where this value a can be written as the root of sum of the squares of a and b, that is a square plus b squared. Also this value phi, phi is the phase actually, it can be written as tan inverse b by a. And from the above equation, you can say that the constituents of the medium at different positions execute SHM. You have studied in the chapter oscillations. Okay. Now from this above equation, it can be used to find the displacements of all the elements of the string as a function of time. That means at this particular time, where does the wave reached, or what is the position of the individual particle, such a particle at a particular time. These things you can find out from this relation. And also it can tell us the shape of the wave at any given time and how that shape changes as the wave moves along the string, and hence how the wave progresses. So these all facts you can take or you can note from this relation. Understood? And this is for positive x-axis, and if you are noting it for negative x-axis, you will get the expression as y of xt is equal to a sine kx plus omega t plus phi. This is for negative x direction. Understood? So by noting this relation or by viewing this relation, you can identify the position of the particles in a time t, then to find the displacements of all the elements of the string as a function of time. Then you can tell the shape of the wave at any given time, how that shape changes with time. So these things, how the wave progress, these things you can note with the help of this equation. Clear? Now, in this expression, you can, once again I am explaining the terms. This is actually the displacement of the vibrating particle as a function of the position and time t. Now a is the amplitude of the particle. Now omega, you have studied, it is the angular frequency. Omega is the angular frequency. Now x, again it is the position of the vibrating element. And here you can see k, which is the angular wave number. So this term, that is kx plus omega t plus phi or kx minus omega t plus phi, you will call it as the phase of the vibrating element. Phase of the vibrating element. Understood? Now phi is a phase constant at x equals 0, t equals 0. So just understand the terms. A is the amplitude, x is the position, k is the angular wave number, omega, you know angular frequency, t time, phi means what? As phi is the phase constant at x equals 0, t equals 0. Then yxt is the displacement of the vibrating element. Okay, a is the amplitude. So this is the expression for a progressive wave, that means displacement relation for a progressive wave. Now there are certain terms related to waves that you have studied in your smaller classes, like amplitude, then wavelength, isn't it? then time period, angular frequency, angular wave number. Some terms you have to study with respect to this portion wave, and now we are moving to that. So let's first discuss the term amplitude. So what is amplitude? You know, this is the representation for a wave. Okay. And you know how to write the expression, that is y, that is the displacement, is equal to a sine kx minus omega t plus phi. And I told that this is actually the amplitude of the wave. And in the diagram, if you are asked to represent, or if you are asked to denote the amplitude, how will you represent? It is the magnitude of the maximum displacement of particles from their equilibrium position. That means, suppose if this is the mean position or this is the equilibrium position, you can see that this is actually the maximum displacement of the particle. The particles are vibrating and the particles will reach this position, which is the maximum displacement or the magnitude of the maximum displacement from this mean position or from this equilibrium position. Okay, and that value is known as amplitude. Understood? So here in a wave, you can see there are two portions, one in the upper direction, other in the lower portion. This is the maximum value of displacement in the upward direction, and this is the maximum value of displacement in the lower direction. So this is A, you can take it as A, and since it is negative, you can take it as minus A. In the lower portion, even though it is maximum value, it is having a negative sign since it is in the opposite direction. So small letter A, positive A and minus A. In between these values, the displacement varies. The displacement varies between where A and minus A. Understood? Here A represents the maximum displacement of constituents of the medium from their mean position. Clear? The displacement y may be positive or negative, but A is always positive. It is called the amplitude of the particle. Understood? Now, as I told, this value, that is kx minus omega t plus phi, is called the phase of the wave. Is called the phase of the wave. And you can say, how will you define phase? Phase means you can denote it as the argument of, you have studied in maths, argument of sine or cosine function. Argument means in this way, if you are writing like sine of that value, that is known as the phase. That is known as the argument, and here you can say that kx minus omega t plus phi is the phase which appear as the argument of sine. It can be sine function or cosine function. So argument of sine or cosine function, that is known as phase of the wave. Okay. Now the next term is wavelength. So we have discussed amplitude and phase. Now the third one is wavelength of the wave. Wavelength, as you know, it is the minimum distance between two particles having the same phase. Minimum distance between two particles having the same phase. Either you can say that it is the distance from this point to this point. That is correct. Also you can say the distance between two crests or the distance between two troughs. That is also correct. So, the distance traveled by a wave during the time in which any particle of the medium completes one vibration. Understood? That is the distance starting from here, it will complete its one vibration or one oscillation at this point. This distance you can call it as wavelength or otherwise you can say that it is the minimum distance between two particles having the same phase, means here from here to here or from here to here. That is also known as what? Wavelength, and is denoted as lambda. Wavelength is denoted by lambda and unit is meter. Understood? That is known as wavelength of the wave. Clear? Now, period, time period. Time period, you know, the time period means time taken by a wave to travel a distance equal to one wavelength. This is one wavelength. This distance is one wavelength, and time taken to complete this one vibration or complete this one oscillation, you will call it as the time period. And time period is actually the reciprocal of the frequency. Time period is the reciprocal of frequency. Understood? Frequency, what do you mean by frequency? Frequency means the number of vibrations or number of oscillations produced by the wave in 1 second. So you have discussed time period. Then next one is frequency. So amplitude means maximum displacement of particles from their equilibrium position. Phase is the argument of sine or cosine function. Then wavelength means the minimum distance between two particles having the same phase is called wavelength, or the distance traveled by a wave during the time in which any particle of the medium completes one vibration about its mean position. That is also known as wavelength. Then next one is time period. Time period means the time taken to complete one vibration or one oscillation. Next is frequency. It is the number of complete vibrations or oscillations produced by the wave in 1 second. And frequency and time period are how? They're inverse. That means reciprocal of frequency is actually time period. Okay. So that's all about the terms related to a wave. Now we are moving to the speed of a traveling wave. Okay, how to find the speed of a traveling wave.